You're right. It should be on to the right of this.
Number 4.
Oh, number 4. Oh, okay.
Number 3 is pretty straightforward. Yeah.
Okay, number 4.
Straightforward if you make sure to differentiate between radius and diameter. Otherwise, it comes out really weird. You make mistakes.
Okay, so you can do problems like this. You can treat this as 2 separate bodies. I guess you'd have to divide up the masses, which would be kind of a pain. So let's just calculate the centroid of this thing. So I'll break it up into this. You could break it up a couple different ways. I'll call this 1 and this 2. And I guess I'll put the coordinate system, the origin here. And so for body 1, for both of these, we're going to calculate the area and the centroid. The area of 1 is 0.1 times 0.3. And the centroid is 0.150. And then for body 2, the area is 0.04. And the centroid is, okay, so it's going to be down 0.1. So that's going to be negative 0.05 for y. And for x, it's going to be 0.4. Does that look right?
Yeah.
And the total area is just the sum of these, so 0.07. So we have 1 over 0.07 times the quantity 0.03 times 0.150 plus 0.04 is the area times 0.4 negative 0.05. And distributed load problems look like this. So it's just any old rigid body statics setup. But instead of the forces happening at specified points, you have these forces applied over some, for us it's always going to be 2D spread over some distance. And it'll be given as like at the highest point of this distributed load is 2,000 newtons per meter. Okay, so it's forces spread out over a distance. And it's always the case that if you go to enough precision for a problem, every load is a distributed load. Okay, so I want to just to sort of understand what's going on. I want to make a connection between this and something that you're used to thinking about. So let's think about in this column of a table, let's think about distributed load versus the total applied force. And in the other column, let's think about instantaneous speed versus distance traveled. And I just think this is a nice way to kind of wrap your head around what's happening with distributed loads. So an instantaneous speed. So if you think of something having some finite instantaneous speed, how far does it travel in a single instant? You know, the answer is none. So an object moving at a finite speed travels zero distance at any, instant. In the same way, a distributed load applies zero force at any point. Okay, so like in this picture up here, like this distributed load, what's the total force that it's applying to this beam right here? Nothing. Okay. And connected to that, if something's going at a finite speed and you want to travel a finite distance, it has to go over some elapsed time. Okay, so to travel a finite distance, you need to carry a speed over a finite time interval. So the same as that, for a distributed load, to apply a finite force, it needs to act over a finite distance. If you're trying to visualize what a specific instantaneous speed means, so this is kind of like an intuitive meaning of instantaneous speed. If you held that speed for 1 unit of time, then that gives you the distance you would travel. Okay, so, what does 50 miles per hour mean? It means if you stayed exactly at 50 miles per hour for 1 hour, you'd go 50 miles. And it's the same thing with the meaning of distributed loads. So the meaning of a distributed load is if the distributed load were constant over 1 unit of distance, that's the total force that would be applied. Okay, so let's look up at this example here for a second. Let me just give this a length. Let's say this is 3 meters total. Okay. So this says at the greatest point of that distributed load over here on the right, if that was held constant over these 3 meters, we'd have a total force of 6,000 newtons. You can see that the 2,000 is the highest that distributed load is. So you can tell just from looking at this that the total force applied by that is something less than 2,000. Okay. And then the last one, this is a more mathematical one, but the total distance traveled is the integral of the speed dt, as long as you don't change directions and stuff. And it works the same way for a distributed load. The total force is the integral of the distributed load, but this time with respect to x. In order to use a distributed load in Newton's laws, you first have to define an equipolant system. Remember what an equipolant system is? Anybody want to try to define it? So an equipolant system for a rigid is always for a rigid body, and it says it's a different collection of loads, but a collection of loads where the behavior is the same. Okay, so before we can use a distributed load, we have to define an equipolant system where the distributed load is replaced by a single force vector acting at a single location. And this is important about making this switch. You can't switch to a single force until you choose a body to isolate. This is going to be a really big deal when we get to internal loads. Okay, so don't think like I'm gonna choose this equipolant system and then use it forever after in all my free body diagrams and whatever. First, you have to choose the body to isolate. Then, once you're treating that as a rigid body, then you can make this switch. Okay, so the magnitude of the equipolant point force is the area of the distributed load and the location of the equipolant point force is the centroid of the distributed load. Okay, so we're going to think of this distributed load as a triangular shape. It has an area, and its area, if you do the units, would be newtons, or whatever units of force you're using, and it would have a centroid, and that's where the point force is applied. Okay? Any questions about that before I just show some examples? And so,
No, I'm just stretching.
Okay. Okay, so let's start with the simplest example we can come up with, and then we'll go on from there. So first, let's say we have a beam. And let's say that, well, I'm gonna just right away say that this beam has a mass of, let's say 100 kilograms. We'll say that this is 2 meters long. And we want to calculate the reaction loads. Do I want to do the, sorry, erase that. Let's not, we do want to calculate the reaction loads, but let's not think of it in terms of weight yet. I'm just going to give you the distributed load here. We're going to see later when we get to internal loads in beams that we're going to have to treat weight as a distributed load, but for now it's not really an important thing to worry about. So let's say this is a uniform distributed load, and let's say that the magnitude of this is 3,000 newtons per meter. Okay, so start with a free body diagram. The roller on the right, that force is perpendicular to the surface. The pin joint on the left, I'll call this RB. The pin joint on the left provides a full force vector, no couples. I'll call this the vector RA. Okay, and then we have this distributed load. So I'm going to do this free body diagram in a couple different steps. Yep.
So this would be a really large amount of force for it, but would this represent like a fan over top of our object or something?
Yeah, it could be something sitting that's distributed over the whole thing, or a pile of something, or like I said, it could be the weight of the object too. You know, eventually, uniform distributed loads like this will always represent weights. Okay, so let me draw that distributed load shape. Not drawn to scale, but the height is 3,000 newtons per meter. The width is 2 meters. And so the area of that shape is 3,000 times 2, so 6,000 newtons. And the centroid of that shape is right in the middle. Since this distributed load force is straight down, we don't care about the y position of that centroid. We only care about the x position. Okay, so this location here is 1 meter from either end. And so now I'm going to replace this distributed load we still have this stuff. This hasn't changed. But I'm going to replace this distributed load with a downward force at the middle of 6,000 newtons. And now that's an easy problem. We can, write out a table for it. I'll put the about point here. So RA, the row vector is 0. The force is RAX, RAY. Cross product is 0. The 6,000 Newton force is at 1, 0. I'm not messing with the height of this at all because that's just a downward force, so we can put it at any height without changing the problem. The force is 0, negative 6,000. And so the moment is negative 6,000. And then the force RB, again, that's vertical, so the height doesn't matter. So I'm just going to write this as 2, 0. The force is 0, positive RB. And so the moment is 2 RB. So we get 3 equations. The first one says RAX is equal to 0. The second one says RAY plus RB minus 6,000 is equal to 0. So I'm going to put it on the other side as positive 6,000. And then the third equation says 2RB is equal to 6,000. From this one, you can see RB is 3,000. Then plug that in here, and you can see RAY is 3,000. And that's it. Any questions about that? By the way, this is sort of an easier way to think of you know, a quicker way with beams. You always can write out that table, but we're going to see a lot of horizontal beams. And so just think of, you know, for each moment, think of the moment is going to be plus or minus the distance from the about point to the force. And then that force, I guess we're only going to be thinking about the y components of forces. This is not a derivative. X components of forces aren't going to produce any moment along a horizontal beam. This is the distance to the about point. And then what about the plus or minus? Then you just have to think about those forces in terms of would it cause a clockwise or a counterclockwise rotation around the about point. Okay, so in this case, instead of writing out the table and stuff, for the moments, we can just say RA doesn't produce any moment around the about point because it's at the about point. Okay, what about the moment for the 6,000 Newton force? So we have plus or minus 6,000. What's the distance from the about point to the 6,000 Newton force? 1. Would that 6,000 Newton force cause a clockwise or counterclockwise rotation around this hinge? Clockwise, so we want the negative. Okay, and then we'll go to the next one, plus or minus the force is RB. What's the distance from the about point to RB? 2. As drawn, would that RB produce a clockwise or counterclockwise rotation? Counter. So we want the positive here. And now just set this equal to 0. And then you don't have to. So for these horizontal beams, you know, in a lot of cases, setting stuff up in terms of vectors and doing the cross product is the quickest way. But with horizontal beams like this, it's not really worth going into the vectors. You can get through these just a lot quicker by just thinking of the distances. Okay, any questions about that?
So then you just look at your free body diagram to figure out the Newton's second law.
Yes, that's right. Yep.
So you just write it right off.
Yeah, you can just write it right off of the free body diagram, exactly. Yeah. Okay, so let's just bump it up to something a little more complicated.
What about like a ratchet strap holding on a box?
Uh-huh.
So wouldn't the tension, so the distributed load would be determined by the tension in the ratchet strap?
So describe what I'm drawing here.
It's just a box with
Uh-huh.
two tensions.
Okay, yeah, holding it down.
Yeah, holding it down.
Okay. So yeah, if you had if you had a box like this and you had a strap like this,
Yeah.
um, you'd probably draw your free body to be like this. And so then the free body diagram, you could think of it as like include the strap that goes over the top and a little bit of the straps coming off. And then you would just have point forces like this.
Probably be like parabolic, right? Something like that.
Oh, the distributed load?
Yeah, like lots of
Well,
things on the corner.
you know, you wouldn't even have to, if you included that. So I'm including the top of the strap in that. And so then that's all internal and you don't even have to worry about it. But yeah, I guess if you wanted to, so I would do it like this first just to calculate the tension in that strap. But then, right, if you're trying to figure out later like stresses and stuff in the top of the box, then you could use those tensions to try to figure out, yeah, some kind of, I think maybe you'd have to do that just sort of experimentally. I'm not sure. I can't think of a way to figure out what the distributed load is. But yes, so for a distributed load, yes, you're right. That's some kind of, who knows what that would be. I'll bet it would be a high force there and drop down and then, I don't know, maybe something like that. And then you'd have to deal with a distributed load that looks something like that. Yeah, I don't know. That's a total guess, but
I guess it really, I mean, it would be symmetrical, so you could just say it was acting in the middle.
okay, so if you're trying to figure out, so if you're just trying to figure out the tension in that cable, then you could do it like this middle picture, and that's the end of it. If you're trying to figure out how likely that is to damage this box, then you have to treat it like it's a deformable body. And then you can't use equipolant systems for that anymore. So then you'd have to calculate what are called internal loads and go from there to stresses and strains. We'll get into internal loads later on. But that is like the distinction between whether you're treating this as a rigid body and trying to calculate external things, or whether you're treating it as a deformable body and trying to calculate internal things. Okay, I'm erasing this.
A good thought experiment.
Yeah.
Question.
Nope. Okay, so the second example, so let's say we have a cantilever beam with a fixed joint with the wall and a triangular distributed load like this with a maximum value of 10,000 newtons per meter. And let's say that this length is 0.5 meter. And we want to know what are the reactions at the wall. Well, first I'm going to draw a free body diagram with that distributed load still in there. You don't have to take this step, but I think it can help avoid confusion sometimes, especially early on. Okay, so for a fixed joint, we know that there is a force vector. I'll call that R. And then there's also a couple preventing rotation. And I'll call this MR, like reaction moment. And then we have the distributed load. And now that we've chosen the body to isolate, we can represent. So the thing is, once you choose the body to isolate, you're always treating your free body as a rigid body. Okay, that's true in deformable body mechanics too. Everything. So we've chosen the body to isolate. Now we can represent this as a point force. So let's think of the distributed load shape. It has a base of 0.5 and a height of 10,000. And so the area of that triangle is 0.5 times 10,000 divided by 2. That's just the area of a triangle. So that's 2,500 newtons. And then what about the centroid of this shape? Well, this is a right triangle. And so we know this distance is base over 3, and this distance is 2 base over 3. Okay, so we know that from the left end, it's 2/3 of the length of the beam where this is located. We don't care about the vertical position of that centroid. And so I'll draw the free body diagram again. But this time I'm going to replace that distributed load with a point force. The total value of that point force is 2,500 newtons. And this distance is 2/3 of 0.5, so 0.3 repeating. And now this is the free body diagram we're going to do the calculations off of, with the equipolant point force in place of the distributed load. Any questions about that free body diagram? Okay, so from a free body diagram in 2D or 3D, you can always just write out the table and do the cross products and stuff. I think for horizontal beams, you'll want to get used to just doing it kind of in terms of those distances and just thinking about the directions. So you always could use the table. But it's not the fastest way. For horizontal beams. Okay, so for X forces, we just have Rx is equal to 0. And actually, yeah, that's fine. But this is the X equation from Newton's second law. The Y equation says Ry minus 2,500 is equal to 0. And the moment equation, I'll put the about point here. Do we have any moment produced by R?
Yes.
No. By because I put my about point at the place where R is.
Oh, sure.
It just depends where you put your about point. You know, you can always choose which one of those forces is going to have zero moment. But I'm putting it where R is, so we got 0 for
But that doesn't necessarily mean that MR is 0.
MR is going to just be MR.
Yeah.
That always plays itself. You don't have to think about any about points or anything. That just goes in there. And then plus or minus 2,500 times the distance, 0.3 repeating. That's all of them. And then would that 2,500 Newton force cause a clockwise or counterclockwise rotation around that about point? Clockwise, so that's negative. And so we get MR minus, I guess that would be 833.3 repeating. Yeah, is equal to 0. And so this force R is 0, 2,500. And this couple is 833.3 repeating Newton meters. Any questions about that?
Are these always going to be linear distributed loads?
I think we might have a couple in this section. I'm pretty sure we have 1 or 2 in this section where they're not linear. But I think I gave you, they're always going to be, so remember when I gave you the centroid information for all the 2D shapes, I gave you areas and centroid locations for at least, for a couple of nonlinear ones, a quarter circle, and then also a part of a parabola. And so I think you do have to use those formulas once or twice in the problems. Yep.
Is there like a similar concept in physics, like force density or something like that?
Force density. I mean,
Or is it only really in statics?
I'm trying to think. Mathematically, this is probably pretty similar to calculating forces in a, let's see. So what's the relationship between,
Or is it work?
so force, hold on. Okay, so force is negative derivative of the potential energy with respect to x. And so if you're trying to calculate a potential energy function, you can do that as the integral of the force dx. And so maybe if you've seen math similar to this, it might have been when you were talking about potential energy functions.
Okay.
Yeah. The math does look sort of similar. Any other questions? Okay, well, that's it. I'll give you some distributed load problems to work on.